we start?
Almost 8.
Hey, welcome everyone. This is our Starry Night, the third show, and today we have six panelists: myself, and Ivan, and Alex, and Yannick, and Jane, and we have a new panelist today, David Aquilio. He is also one of the very, enthusiastic problem posers, so he has lots of good problems to talk about. And today we are going to talk about four problems. And the first one is by Alex and Yannick. We are going to follow up with what we did last week, right? It's about that sequence problem. And we have two follow-up questions, and we will go from there. And Ivan, you want to share the screen with us, with the problem statement, or what?
Oh,
You are
sorry,
muted.
I'm muted. So it was about cooking problem, right, guys? Do
Cookie.
you remember?
Yes.
Cookies. Okay. So, and that was actually the statement, right? Number one is the statement. We have a sequence of positive integers, 10 numbers, and what do we know, Yannick? You should.
Yeah, so basically we want to find a sequence of 10 positive integers that are in, I think, decreasing order. I mean, it doesn't really matter here. But the point is that if you take any consecutive subsequence, like say from the fifth item to the fifth number to the eighth number, then their average is also an integer. So the original question asked for like, if we require all the numbers to be positive and strictly decreasing, then what is the smallest possible value of the sum of the 10 numbers? And in case you guys didn't remember, the construction we came up with was 19, 17, 15, 13, all the way to 1. This is arithmetic sequence with all terms being odd. So like if you take the average, you'll see that it's the median of median, which is always an integer. Yeah. And last time Alex asked the question of like what do we do with second minimum possible value? Of course, there's a cheat that you can just add 1 to every number, but we don't want that. So instead, we require that. The first one, I guess the order switch, but increasing is probably easier to reason with. So the first term must be 1, and yeah. So I mean, again, like we can just like double the common difference. We have 1 and do 1, 5, 9. 13, etc. That will also work.
So
and yeah,
1, 5, 9. We need them to be all odd, right?
Yes, because we need every two because the average of every two consecutive terms is an integer. We need them to have the same parity, and since the first one is odd, all of them must be odd.
Okay.
Yeah. So it's like not so it's not obvious how to show that like this is actually the minimum. So to start, let's think of something that may help simplify the problem. Let me just make a whiteboard, I guess. Hopefully you guys, let's see, okay, whiteboard. Aha. So we originally have the minimum sequence 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. And then we have this, and then we have any sequence L, any other sequence S1, S2, to S10. And we also have a conjecture sequence 1, 5, 9, 13, all the way to I think 37. Yes. Okay. So having these numbers are a little bit hard to deal with, but we notice that since we require the numbers to be strictly increasing, and each number must strictly so we must have that each number must go up by 2 each time, and we also have that the first term is 1. So one thing we can think about doing is to subtract two sequences. So let's think about the sequence S1 minus 1, S2 minus 3, S3 minus 5, S10 minus 19. So what this does is we basically subtracted two sequences. We know that S1 is 1, S2 must be at least 3, S3 must be at least 5, all the way to S10 must be at least 19. So we know that all of these are non-negative. Moreover, we know that since each number must go up by 2 at each time, at least 2 each time, we know that this sequence is actually, in fact, non-strictly increasing. So basically, now we kind of simplify the problem to finding a sequence where the first term is 0. The sequence is non-decreasing and also satisfy the original property. Why does it still satisfy the original property? Because if we take the block of all the because if we take any block of the differences, the average is basically the difference between the two original averages. So it's still a difference of two integers. So
that's the cool thing about your sequence, right? If you subtract them, that average property got preserved.
Yeah. Yeah. So what our conjecture sequence become is 0, 2, 4, all the way to 18, which is I guess a nicer sequence to think about. And since we want to we want to minimize this, we still want to minimize this sum because we subtracted a constant from the sum of the sequence. Yeah, and basically we want to avoid the case where all of them are 0, which basically gives us the original sequence. So let's think about like how do you beat this sequence? How do you beat 0, 2, 4 all the way to 18? You have to have somewhere where it does not increase at all, right? Because like if it just keeps increasing, we know that it still has to keep increasing by 2 each time. Then we just have this sequence or something worse. So somewhere in the middle, we must have like two numbers n and n. So let's think about what comes next. What comes next must be at least n for sure. So it's n plus something. This question mark I wrote must be an even number because it must be at least because it's different. It must be the same parity as with the previous number. Moreover, we must have that 3n plus question mark because we take if we look at the average of the three numbers, 3n plus question mark divided by 3 must still be an integer, which means that question mark is also divisible by 3. So which means that we have the question mark is divisible by 6. So once we have question mark divisible by 6, let's look at the next number. The next number must we also write n plus I'm not using a good variable here. Let's use x. So for similar reasons, x must have the same parity as the question mark, and question mark plus x must also be divisible by 3. So x must be divisible by 6 as well, which means that everything that follows is a multiple of 6. In fact, we can run this we can run the argument in the other direction as well. To show that all the numbers must be congruent modulo 6. And also we know that the first number is 0. We must have that the entire sequence must be a multiple of 6. So that's one key observation that we have here. Let's see. I think I can clear everything. So basically we have an observation. So if better, all numbers are multiple of 6. So let's go back to the original sequence. So the target to beat is this. We also know another property of this sequence. So let's look at the first 5 terms and then the next 5 terms. We know that the sum of the first 5 terms must be a multiple of 5. The sum of the next 5 terms, the second term to the sixth term, must also be a multiple of 5. So which means that if we take the difference, then we have that this is S1, this is S6. Now, if we take the difference, we get that S6 minus S1 is divisible by 5. Now we know that like if we want to beat the sequence, we must have S6 being divisible by 5 and also divisible by 6. So if S6 is not 0, it must be at least 30. Well, if it's at least 30, we're in trouble, because if S6 is 30 and it has to be non-decreasing, then everything that follows has to be at least 30. And we know that the sum is equal to 90. That's our target to beat. So this cannot happen, because because this will put us already at 150. That's not good. So S6 must be 0. And we also can similarly make the observation that S8 minus S1 is divisible by 7. Yeah. So if S8 minus S1 is divisible by 7, then S6 is either 0 or greater or equal to 42. Again, that will put us in trouble.
S8, not S6.
Oh, S8, yes. Yeah, thank you. Yeah. So again, this cannot happen, because this will make us put us at 126. That's also not good. So this must also be the case. So basically what we have here is that if we have a sequence to beat this, then it must be 0, 0, dot, dot, 0, with two terms left. And at this point, like we'll have like greatly simplified our casework. I think we can actually try one more. S9 minus S1 is divisible by 8. So S9 must be 0, 24, or 48. I think if you're 24, you're in trouble as well. Yeah. So at this point, we basically reduce the problem from like bashing over all possibilities. I think before the show, we were even talking about running a computer simulation, but right now, like this is something that is feasible to do by hand. And I guess the moral of the story is that, in fact, I don't think we even need to do casework on this, because we also have S9 minus S2 is divisible by 7. Mm. Yeah. So 24 doesn't even work, and it has to be something really huge. So this must be 0, and for similar reasons, this must be this must be something huge or 0. But if everything is 0, then we have the original sequence 1, 3, 5, etc. That's the first smallest. That's not the second. That's not the second smallest. So basically, this sequence, or like the original counterpart 1, 5, 9, etc., gives us the second smallest sequence. Yeah. So this is something that I thought about after the show, after our first show. I think. Yeah. I just want to talk about the second question you asked.
I think, Yannick, let's do this. This is already a very good discussion, because you tell us how do you think about this, and reduce to these cases, and then you have much less casework to talk about. I think that part 2 is also very good for our audience to think about, and then we can come back next week and you can talk about this extension again, right?
Yeah, that also work. Yeah. Okay. I think something I talked about here will help with that problem as well.
Yeah, I guess here basically one thing Yannick did was he emphasized that basically instead of having sums of lots of numbers, he only has a difference like S6 minus S1, right? Yeah. So somehow when you take 5 numbers in a row, like considering the sum of those 5 numbers being divisible by 5, well, that's not a lot of information. But knowing that S6 minus S1 is divisible by 5, well, that just means that like they're the same, like they have the same remainder, like when you divide by 5, right? So that's actually a lot of information. So you can think about like how to convert these like more complicated conditions, combine them together into simpler conditions, like S6 minus S1 is by 5. I can even say like S sub X minus S sub 1 is always divisible by X minus 1, right? Yeah. For the same reason.
And that will help you to do that second part. Okay. So let's move on a little bit. So Eva, are you ready for our second question? Are you ready for the poll? not.
Oh, if I say, oh, I need to stop sharing. Right, sorry.
Okay.
Okay, and I'll make a spotlight on this problem. So this is the next problem. So you guys can read it. It's an algebra problem about polynomials. So we want to give you some time to work on it. And we'll try our poll. I hope.
Should we vote or we should not?
You're not allowed.
We cannot vote.
Okay.
Yeah.
Because I can provide at least a variation for wrong answer.
If
Also,
one
you
of you
missed
guys,
James Lin. Yeah.
oh, sorry, James Lin, I misheard. My bad. I apologize. Okay, so 40% voted. And we end our poll here. So now, guys, I share results. Can you see them?
Where is it?
I don't think I can.
I can't see it.
Attendees are now viewing poll results. So attendees can see.
Okay.
Okay, we
I
cannot.
hope. Yeah, I don't know why panelists
No.
cannot.
Attendees are telling us in chat they can't see it either.
Huh.
Well, okay, let me do this way. I'm doing very old school. I'll just print results and show it. I cannot do it. So 23% Mr. Funk, 26% David Altitio, 10% Yannick Yao, 10% Ivan Borsenko, 15% James Lin, and Alex Song 15%. So they think it's by David, and they are right. So David, let's start with your problem.
Yeah, sure. Let me just get stuff screen shared because that's easier for me. Share screen. This whiteboard app that I find easier. Can you guys all see this?
Yeah.
Cool. Okay. In the meantime, I'm going to put this here and then this. Okay, so
I can tell you guys, I tried this problem yesterday, first time. I never saw it before. It's actually very cool. So
okay.
And I also like your first comment yesterday too, you know.
Hold up. Something I'm just trying to get this thing to there we go. I think this should work now. It was just my screen was doing this weird thing where it was like auto rotating and something weird was happening. Anyway, so we have this thing. It's suppose P is a cubic polynomial satisfying P of 0 equals 3, and this nasty inequality for all x and r. Determine all possible values of P of -1. So
I thought you proposed this problem. How can the inequality be nasty?
I just didn't want to. I didn't want to list out. I didn't want to say out the whole inequality because that wouldn't be enlightening.
Alex never thinks that inequalities are disgusting.
Okay, but you don't actually think this inequality is nasty, right? It's
No, I don't.
It's quite a good inequality. It's 0 on one side. It's a 1 multiplication. You know, it's not a bad.
Right.
Inequality.
I just didn't want to say the inequality out loud. So I think the first thing you should probably notice is that solving for P of x algebraically is going to be pretty hard. At least I don't see a good way to do it. But as Zooming noted, this condition on the left-hand side, this condition that this product is almost 0, has a very natural reinterpretation. And this reinterpretation is, well, what does it mean for a product to be negative? It means that one of these two terms, so I have this red term over here, and this blue term over here.
they have opposite sides. Yeah.
Yeah, for every single value of x, this term, either the red term is positive and the blue term is negative, or non, or they could both be 0, or the other way around. So I think it might be
one of very critical comments, and then you just you immediately covered it up.
I'm going to get to that later. So let's call this polynomial here. I mean, the polynomials themselves probably don't have too much of use. We're going to call this red polynomial q of x and this blue polynomial r of x. Then we have either two cases, right? I mean, it may seem like we have a bunch of cases, but in reality, only two things can happen. So the first case is if q of x is at most r of x, then in fact, p of x has to be sandwiched in between the two, like this. Because certainly p can't be smaller than q, otherwise both terms would be positive, and it can't be greater than r, because otherwise both terms would be negative. No, both terms would also be positive.
So the q of x and r of x do not include the negative minus p of x, right?
Yeah, q of x, I should specify, q of x is this thing, and r of x is this thing.
I see.
I just don't want to write out the polynomials all the time.
Sure.
We need to do that later. And then similarly, if r of x is less than or equal to q of x, which is the other thing that can possibly happen, then r of x is actually between. And so you may think that I've written something redundant, but in reality, the ordering of r and q doesn't matter, and it really tells us two things. So the key idea is that the graph of p is between the graphs of q and r.
And if those have intersection points, p of x should go through intersection points, right?
Yes.
Okay.
I was actually going to get to that, but yeah, that's the that'll be the key observation. So let's actually graph these. Let's actually look at the graphs of q and r, just for because we might as well have a visual. Visuals are good, especially when you're doing graphs. I don't know how you have a graph without a visual. Okay, so I don't want to like specifically compute these points, but we can at least do some nice bookkeeping in terms of where these points are. Okay, so at x equals 0, blue guy is 4 and red guy is 1. So blue is going to be up here and red guy is going to be up here. Okay, and then let's do another one. Let's say x equals 1 give me what I want? Will x equals 1 give me what I want? Does x equals 1 will not give me what I want. Let's try x equals 2. What happens when x equals 2?
8 minus 4 plus 1.
8 minus 4 plus
5.
1 is 5. And what about the blue?
16 minus 20 plus 4.
This will work. This will give me what I want. Okay. So here, blue is 5 and red is 0. This actually gives us everything we need.
What?
I'll explain later. So what do we know about the graphs of blue and red? Well, they cross at this point. They cross somewhere in here. I don't know what the actual thing looks like, but it's going to look like this. Now, the key observation to make here that makes things a little bit easier is that the coefficient of r is 2 and the coefficient of q, the leading coefficient of r is 2 and the leading coefficient of q is 1. So we actually know what's going to happen to these polynomials. They intersect at two other points, namely somewhere up here. I don't know what the exact shape is going to look like, but the point is, no matter what happens,
faster, 2x
blue goes faster. So maybe you might have something like this. I don't know. This is a terrible drawing, but like
it's cool. It's cute. Yeah. So we have 3 intersection points actually.
But those 3 intersection points are critical now, right?
They are super critical. Yeah. In fact, what do we know about P? We know that the graph of P lies in between the graphs of Q and R. So that means that if we look at these intersection points, P also has to pass through them. Yeah. Something like this, I don't know. Like that. Which is cool, because when combined with P of 0 equals 3, we have a unique cubic now. Of course, there's still one small issue. I don't know if actually computing these points is going to be reasonable, but we'll get back to that later. The point is we don't actually need to, because how can we encode the condition that P, Q, and R all have 3 common intersection points? Well, P equals Q implies that P minus Q equals 0, and P equals R implies that P minus R equals 0. So what do we know about these roots? We know that P minus Q has 3 roots. It's a cubic and it has 3 roots. Cool. We know that P minus R is a cubic, or at most a cubic, and it also has at most 3 roots. So these polynomials actually have to be the same up to a constant. So we know that there exists some constant C such that P of x minus Q of x is equal to C times P of x minus R of x. And if you do a little bit of work after this, you'll see something interesting. Assuming I did this correctly, you should get that P. Did I do this right? Hold up. Is this correct? This should be correct.
Yeah, I think.
Yeah, I think maybe the way I did it, the way I did this was a little different. I did Q minus R at first when I originally wrote my solution. So I'm just going to do this to Q minus R, but it's the same thing.
Well, you have an idea that the difference should be a multiple of the other difference.
Right. I just want to write, I'm just doing it this way so I can write this result in a very specific form to highlight actually what's going on.
Okay, but we can just realize the idea. Why the C will be there? Because the rest is a multiple of these 3 black roots, right?
Yes. Actually, I'm going to do something a little bit different.
So
I'm trying to get into a very specific form.
Okay.
Trying to get into a very specific form. So I'm going to do this as R of x and Q of x instead. The reason for this will be very apparent.
Mm-hmm.
So the point is, once you get this, you get that P of x is equal to C times R of x plus 1 minus C times Q of x. So if you're familiar with linear algebra, P is a convex linear combination of C, of Q and R. And in particular, and this is the thing I find interesting, it's not just that P has these same intersection points. The fact that the 3 intersection points of P, Q, and R all coincide means that the relationship between P, Q, and R is really nice. It's actually just some weighted linear combination of Q and R. And from here, we can finish pretty easily. I don't want to go into all the technical details, but the idea is, now that we have this form, if we look back at the problem statement, we know that P of 0 equals 3. And then, so we can plug in C equals 0 to determine, so plug in C x equals 0 to determine the value of C. And then you're done. I don't want to go through all the computation. I think unless it's something we should do. But I also, at some point, I want to talk about the inspiration behind this problem. So, is that okay with people? All right.
I think the idea is clear, yeah.
The idea should be clear. Okay.
There's also something really nice here. It's like basically, it's kind of like you can sort of count degrees of freedom, right? So you know what a cubic looks like. Cubic is like y equals ax cubed plus bx squared plus cx plus d, right? So you have 4 variables. So if you have something with 4 variables and you have 3 intersection points, that means there's sort of only like 1 degree of freedom, right?
Yes.
So if you already know that you can get this degree of freedom by taking, or convex or just, I guess, linear combinations of R and Q, that sort of says that that's sort of the only thing you can do, just like non-rigorously. Like somehow there's this intuition that like there's this duality between the number of parameters in what a cubic polynomial is and the number of conditions that you give it.
Yeah, that's a good point.
But that's
Okay.
something that you guys can explore later on your own with like linear algebra.
Yep. Linear algebra is actually the inspiration behind a bunch of my problems, but not this one. This one is actually inspired. This problem came about because I was procrastinating on RU apps. Fun times. More specifically, some of you may be familiar with a certain other ANY problem that has a very, very similar flavor. And I actually put it all the way up here. It's this one, 2010 AIME1 problem 6. It has this condition. Let P of x be a quadratic polynomial with real coefficients, satisfying this inequality, and suppose P of 11 equals 181. Find P of 16. So you guys may have seen this problem before, but essentially, if you haven't, I'm going to spoil it right now. Whoops. So the key observation you need to make is to sort of do the same thing. You graph the two polynomials, but there's something very specific about how these two polynomials are constructed.
This problem same axis of symmetry, looks like.
Yes.
You know
what,
so David, I wrote this problem.
Oh, nice.
Very nice.
Nice.
So this is so cool.
Oh, nice. Now we all know this problem is a zooming problem. I actually love it when people. I actually love it when we find out about like problem writers, because I think that stuff is actually really cool. So the point is that when you do this, right?
Yeah.
You get that both of these polynomials have the same axis of symmetry. I should color them. I should color code them.
Yeah.
They actually have the same vertex.
So the only difference is that constant.
Yep. And so you get that P of x is also of the form C times x minus 1 squared plus 1. Same sort of deal, except now it might not look like that you only have 1 degree of freedom, but if you want to like reference this in terms of Alex's argument, the fact that the two parabolas have the same vertex means that there's a double root there. So you actually lose 2 degrees of freedom when you do this. So the 1 degree of freedom thing still works. But the point is, when I saw this, I mean, it's a nice problem. But I thought that the configuration was, in some sense, maybe not doing as much. Like there's definitely more to this problem. Like I thought that you could maybe see what happens if the parabolas didn't share a common vertex. Like in this case, the problem only works because the parabolas do share a common vertex. What happens if they don't? Mm-hmm. And if they don't, you have to rewrite the condition, but you rewrite the condition like this. And then that's how I worked on this problem.
Yeah, very cool. Very cool.
One thing that I think is worth noting is, I'll be super quick about this because of time constraints. I start off with the quadratics, and in the end, the problems were cubics. Mm-hmm. So why exactly did I go from quadratics to cubics? Because, well, okay, that wasn't my idea, but it was sort of stemmed from an observation I had, which is that this problem, if you try to do the quadratic case, it emits a much less innovative solution. Because in the quadratic case, you can literally compute the intersection points of the two parabolas.
Yeah.
And I felt that the purpose of this problem was to explore this linear combination stuff. And I didn't want, granted, I could choose the numbers to be nasty enough that you don't want to, that you're unmotivated from doing this, but I'm not sure if that's really possible, because given this configuration, once you realize you can just compute the intersection points, this more computational solution is one of those things that, like, okay, this is ugly, but I know it will work. And so it's completely short circuits the original intent behind the problem, which is why I decided to go with quadratics, which is why I decided to go with cubics instead.
Very good. Okay, so David, we will call here, and so you can stop the sharing, and Ivan can go with the next one, right? Ivan, to speed up a little bit, can we skip the poll for this one and just go directly with your wonderful geometry question?
Yes. So, and I'll start immediately from the idea. I will not reveal the question. I hope some people in the chat will figure out what I will talk about. So the problem that I proposed is related to another problem. So the story goes this way. I was preparing some problem set for a training, and I thought, let me give them an example. An example that I had in mind was the following. You have triangle ABC, and you construct two circles, but they are tangent at B and at C to the line BC. And I wanted students to find the length of AP. So this is how I thought, this is the problem I want to give initially. So maybe some of the panelists can have an idea on the spot if you guys are listening.
Yeah, sorry. So you want AP in terms of the side lengths of the triangle?
Yes. Let's say I give you side lengths are 7, 8, 9, for example. Just some random side lengths. How do you find the length of AP if these two circles are tangent at B and at C?
I mean, there's a stupidly overkill solution if you use your BC inversion, but
You got, also the actual definition of P is pretty well known.
Okay, but how do you solve it fast? Any idea?
How do you solve it fast?
Go chase
You can
similar triangles.
You can intersect if you intersect with
You
BC.
go back to the midpoint, right? That's very common, right?
Oh, right. Yeah.
yes.
You go here by the power of the point, you have MB squared is the same as MP times MA, which is MC squared, right? So this is a midpoint. And then once you know each of them is 4, if you know the median of this triangle, then you can find AP. This is kind of...
That's significantly easier.
Yes. So power of the point was the idea that I wanted to test students, and I had in mind, and you can see, guys, the median you can find, 4 squared is x times whatever, the median minus x. Well, you got the point. But I accidentally typed totally another solution, totally another problem. And if you guys recognize, what do you think I typed? Which problem I typed? And what did it end up to be?
That's really cute.
Oh,
Does anyone from the participants think they've seen something similar recently?
hence the side lengths given are correct.
The side lengths were still the same, 7, 8, 9. Well, maybe you don't remember, but it was last year, Amy number 2.
No,
and the only difference...
This is definitely not number 2.
Number 11 is Amy 2.
Amy
Amy 2, problem number 11. And the only difference that circles are tangent at the sides at point A. So what happened when I tried to do an answer key for this problem, I started to understand I couldn't solve it that easily. This trick no longer works. So this is from problem 11, yes, from last year, Amy number 2. So let's say we have 2 circles and they are tangent right now at A, right? So what can we do here? Well, usually if the circles are tangents, it's good to express the tangency conditions in terms of angles, right? So if this angle is x, then this is also x, right? And if this angle becomes a minus x, so is this angle a minus x, right?
Oh, wait.
Because circles right now are tangent to AB at A and to AC at A, right? And this is a 7, 8, 9 triangle. Similar triangles. Yes, indeed, these 2 triangles are similar, and their ratio of similarity is 7 to 9, right? I thought the same way. So if AK is equal to x, then CK is 9, 7 over x, for example, and BK is 7 over 9x. You guys agree?
Mm-hmm. Yep.
But then I got stuck here because I didn't know what to do next.
For what it's worth, when I was test solving this problem,
right? But yeah, but let's not do barycenter.
For what it's worth, when I was test solving this problem back in 2017, I did the exact same thing. I noticed the similar triangles and just got stuck. So I did not solve this problem.
I mean, it can't be too bad, right? Like angle BKC is 2 times angle A, right?
Wait.
Yes, these two angles, this is 180 minus A, right? And this is also 180 minus A, similar triangles. And the angle that Alex is talking about ends up to be 2A. Guys, do you see this?
Mm-hmm. Right, so like maybe there's something more clever, but at the very least, I can compute cosine of A, I can then get cosine of 2A, and then I can do the law of cosines again.
Yeah, so that way should clearly work, right?
So if you know cosine of 2A, you look at triangle BKC, and that's the end of the game.
And then you also have cosine of A, right, on the top.
Yes, cosine of A, you know, is from 7, 9, 8 triangle. Yeah. So that's one way to solve it. I thought to solve it by summing 3 areas, AKB, AKC, BKC. So x times sine 9, x times sine A, x times 9 over 7, x sine 180 minus A. So using the area, like barycentric, but now I use the fact that I know these 3 angles. Because these 3 angles, 180 minus A, 180 minus A, 2A, determine this point.
Yeah. So that is very nice. Okay. So I'm going to tag on this question. Actually, when I look at this question, I have other thoughts too. That will be homework, like we are extending for this Thursday's meeting. We can talk a little bit about this one. I'm going to share with this diagram with you guys. Okay, or Ivan, it's easier maybe just go with your diagram.
Okay.
Yeah. Just go with that diagram. It's fine. The one you just showed us.
This one?
Yeah. This one. Okay. So if you guys want a little bit extension of this problem, and we can do a little bit more. Okay. So now consider this circumcircle of ABC, and then I extend AK to this point. Say whatever you define, AP, for example. Okay. So this is very interesting. AK is equal to KP. So this will be the homework for our students can think about. And this actually, this configuration, this setup relate to one 1997 IMO problem, and then also a recent USMO problem. It's only because last year when I was giving my students this problem, at the beginning I said, wow, I find something new, I can test it for, JMO or something. Then I started to realize, well, this problem looks so familiar to me. Then I realized, oh, that relates to one of the problem I already wrote. So anyway, this gives you some idea about the extension. So think about this geometry configuration and really try to prove AK equal to KP. This is a very good exercise. Okay?
It definitely is not something that's like very new. It's definitely something that, like, if you've done a lot of harder geometry Olympiad problems, like this configuration, this point K in particular has come up quite often.
Yeah.
And then also ABPC is a quadrilateral that has a very special property as well that appears quite often in a lot of geometry problems. Yeah. So this is actually introduction to Olympiad geometry a little bit, which I know a lot of the attendees might not be that familiar with, but definitely, like, a lot of Olympiad geometry is being able to recognize and discover configurations like this one.
Yeah. So Friday, James, you can give a more complete things about this, right? So now
maybe next time.
Next time, yes.
Yeah. So the more of the story here is, like, all geometry problems are the same, right? Which means that you only need to do one geometry problem, and then you've done them all. So then you can do other problems like algebra.
What Alex is talking about is complex bashing. He can complex bash every problem the same way.
No.
Successfully.
This problem is the same as this IMO problem. This configuration appears everywhere. All geometry problems are the same. That's what you guys are saying. That's what I'm hearing.
I'm not saying all geometry is the same. I'm saying that there are select configurations that will help to recognize. I'm not saying that it's unfair to extrapolate to say all problems are the same.
I think right now what's popular, moving points. It's right now the most fashionable thing.
Have people learn basic stuff first, please.
Yeah, this is a good basic thing to do, right?
Yeah, I don't think even I know all the basic stuff.
Oh yeah, so moving points is a fad that started in like after my time, and my time was like 2 years ago. So
it's okay.
It's bad. Now there are people who only know how to use moving points to solve problems. So they miss like JMO ones because they only know moving points. It's toxic.
It's sad.
It's the new fad. Evan can tell you about all the fads that have come and gone over the years. Very centric. Then
complex bashing.
No, that's not a fad.
Points?
Yeah. No, what was the fad after that? Oh, Desargues evolution theorem, dual Desargues evolution theorem. That was
geometry these days are way beyond my comprehension.
That was the fad of like 2017, I think, or 2016.
Yeah, DDIT.
Yeah.
Lots of things to learn, but should we move to the next problem? I guess.
Let's move to the next question. You want to give us a poll for this one? We have time.
Oh, someone asked if they only know how to bash if it's bad. I think Alan Liu solved every single problem in Olympiad geometry with trig bashing and was successful.
They better have their good skills.
Well, you better be good at it. You better be able to solve it. Because the problem with bashing is that like Olympiad problems is if you aren't good at it, if you can't complete them, you're gonna get like zero.
Yeah.
So you have to be like Alex and be able to complete every single. Well, you have to be able to know when you can complete your bashes, but especially if you have a legend like Alex on complex bashing or Alan on trig bashing. These people just never fail.
Still, learn some basics. Learn some basics at least.
Yeah, definitely. This is not normal.
James, can you see the problem? Can you read it for us? You have very.
Sure, I can read the problem. Alice plays the following game. On each move, she may add a stone to an initial empty pile, or she may add the number of stones currently in the pile to her score. She wants a score of exactly 20/20. What is the minimum number of moves she needs to make to achieve this score?
So what's the poll?
I don't think we'll have a poll because I cannot show it to everyone. So we'll do it next time. Sorry, guys.
We have some technical.
Sure, but this problem is from 2020, right? So what competitions happened in 2020? Just AMC, Amy?
None of them.
Oh no, yeah.
Everything's canceled.
Well,
HMMT.
Well, HMMT happened.
It happened. It did.
So we basically modify the numbers here, right? Okay, to meet this year.
Well.
So Alex and Yannick, you guys go.
Sure. Alex, want to talk about it briefly?
Yeah, sure. So I guess the idea is like basically, well, her score like always goes up or like stays the same, right? If she does the first move, then her score stays the same. If she does the second move, her score goes up. So it's like at first you just want to think about like maybe like obviously if you have more moves, then you can get a higher score. Right?
So from S you go to S+1 or 2S? Sorry.
No.
No, you don't double the number of stones.
Or you add the number of stones to your score.
You have lots of piles, right?
Okay, got it.
So when I first see this problem, like I see stones and I see score, and I'm immediately reminded of that the other problem where like you split piles of stone into smaller piles and get points from the product of the piles is split into. I think that problem has a nice idea that I don't know if that would be any related, but like
is there only one pile?
Yeah, there's only one pile. Yeah.
Mm-hmm.
So at first, I think it's like kind of like sure, like if your score is higher, if your number of moves is higher, then you can get a higher score, right? So you can think about maybe like if you only have a fixed number of moves, what's the maximum score you can get? So say if you have like 10 moves, what's the maximum score you can get? Maybe easier, 4 moves. 4 moves. What's the maximum score you can get in 4 moves? But Yannick, you're supposed to answer.
Oh, right. Yeah. So I mean, well, one thing that I'm thinking right now is that like, if you like add a stone, if you score something and then add a stone, like it's probably better to just add a stone first and then do the scoring because then you can score that stone as well.
Yannick, maybe you can open your whiteboard so we can take notes.
Sure, yeah. I could do that. Let me grab my pen real quick. Sure, whiteboard. Yeah. So we'll have two types of moves. One is +1 stone. 2 is score plus equal to stone. Yeah. So what I was thinking is that if you have a type 2 move in front of a type 1 move, then if you just swap them around, then like you're basically the number of stones remain the same, but your score increases by 1 because when you score, like you get 1 more stone to score.
Right. So you made an interesting comment here. It's like you said, when you score, you're scoring that stone, right?
Mm-hmm.
So in fact, you can say something like, say your set of moves, you have some moves like maybe 1, 2, 2 or whatever. You can just write down some moves, right? Basically, it's like for every time you do move 2, you're scoring all the moves once before, right?
Mm-hmm.
So there's something symmetric here. It's basically like it's trying to count a number of pairs of 1s and 2s, such that the 1 is before the 2, right?
Mm-hmm.
So,
yes. Mm-hmm.
so say you have 4 stones. Well, what's the maximum number of pairs of 1 and 2 for which the 1's before the 2? Well, if you have 2 1s and 2 2s, then the maximum is 4. If you have 1 1 and 3 2s, it's 3, right? Mm-hmm. So now you can like think about the more general case where, say there's, I don't know, let's pick a bigger number. Like, let's say there's like 40 moves you can do, right? If you can do 40 moves, then what's the maximum score you can get? Well, let's say x of the moves are 1, and 40 minus x are 2. If you want, I can also share my screen.
Oh yeah, go ahead.
Yeah.
Okay,
sorry.
Whoops. Let me stop my sharing first. Cool.
Sorry. There it is. Here. So let's say you have like 1, 2, 2, 1, da, da, da. And we're saying like we look at the pairs 1 and 2. So let's say we have 40 moves. Let's say x of them are 1s. 40 minus x of them are 2s, right? So maximum. So what's the maximum score you can get? Well, the maximum score you can get is like you're counting the number of pairs of 1 and 2, such that 1's before 2, right? So the maximum is if every pair of 1 and 2 has that 1 is before 2. So the maximum score is x times 40 minus x, right? Mm-hmm. And in fact, why not? Like this 40 doesn't do anything. Let's change it to a y because we can be abstract and it's not that abstract, right? So we want something like x times y minus x.
Hold on, Alex. Can you go back a little bit? Can you explain the 1, 2 part a little bit more? I'm a little bit lost here.
Yeah, so here, basically, your score equals number of pairs 1, 2, such that 1 is before 2, right? This is because of Yannick's comment where he's saying something
yes.
like, he's saying something like every time you do a 2, you're scoring all of the ones before you did the 2.
So this 1, 2 are not neighbors. It's all this kind of 1, 2 positions, right?
Yeah, all of them before. Yeah. So this, sorry, I guess I drew the arrows in the wrong direction, but like this 2 here scores both this 1. This 2 also scores this 1.
Yes.
Yeah. So basically, well, the maximum score you can get is if all of your 2s score all of your 1s, right? Because all of your 2s are after all of your 1s. So the maximum score is this x times y minus x. And we know that x times y minus x is less than, what's the bound on this in terms of y? Well, it's surely less than y squared over 4, right? And this is because I can expand x minus y over 2 squared equals x squared minus xy plus y squared over 4.
Yep.
Right? So you rearrange this and you get, and the inequality, of course, should be non-strict. Mm-hmm. So basically, this says something like, okay, so now we can look at the number 2020, right? So if y equals 90, then x times y minus x is less than or equal to 2025. Move this somewhere else so that it doesn't. And then if y is less than or equal to 89, x times y minus x is too small, right? So now we know that y has to be at least 90, right?
Yes.
And Yannick, you made another comment where you said, if you have a 1 that's after a 2, and you make it before the 2, then your score increases by 1, right?
Yeah.
So why is that? Well, imagine say you have a bunch of stuff here. Let me just draw a bunch of stuff. Okay, so you have a bunch of stuff here, and then you have a 1 and a 2, and then you have a bunch of stuff here, right? So what's your score? Your score is if you have some 2s here, your 2s score this 1, and if you have some 1s here, then this 2 scores all of these 1s, right? And then, of course, within this bunch of stuff, in the left and right, you also have some more scoring. But say you swap the 2 into 1. So say you swap the 2 into 1, right? You swap these two. So now it becomes 2, 1 here. Well, after you swap them, all of these arrows still stay the same because all of the ones that this 2 scores, it still scores, and the 1, it still scores, other than this 2 scoring this 1. So this is the only arrow that disappears here. So that's why your score decreases by 1 whenever you swap a 1 and a 2, right? So initially, if you have 90 moves, Alice can score 2025, and if she wants to score exactly 2020, she just needs to swap a 1 and a 2 5 times, right?
Yeah.
And I mean, of course, you can swap the 2 into 1 5 times. You just swap the first 2. You have 49, you have 45 ones. You have 45 of them, and then you have 45 more 2s. You just swap the first 2 5 times, right? And that gets you 5. If you swap it 5 times here, then that gets you enough. But in fact, somehow it's you can actually prove that you can actually swap the 1 and the 2 25 times. You can actually always swap a 1 and a 2. So you can actually, given any number of moves, you can always get a score of 2020, as long as there's at least 90 moves. So
what are you trying to say in the last sentence?
The last sentence I'm saying is I've shown that if you have 90 moves, then I can score 2020, right?
Yeah.
But in fact, even if I have more than 90 moves, okay, well, it's actually trivial that even if I have more than 90 moves, I can always score 2020 because I can just do move 2 a bunch of times and then do move 1. But I guess the interesting thing is, if initially you have these 1s and 2s, right? And if one of your moves is to swap a 1 and a 2, then you can just keep doing this process until all of the 2s are on the left and all of the 1s are on the right, actually. I felt like that was also pretty cool. That was something. And that's
Alternatively, if you have more than 90 moves, you can start off with a bunch of 2s until you get to exactly 90 moves and then repeat.
Yeah. First I thought it was more complicated, but yeah, you can just do a bunch of 2s, for sure.
Yeah.
Alternatively, you can end with a bunch of 1s because of the symmetry of the problem.
Yeah, actually.
That's true. You could. You'd just be wasting a lot more stones.
No, the stones are already there. She's not creating stones with some geological vision or whatever, right?
That's fair.
They're already there. Just throws them back to the beach afterwards.
I think when I was thinking of the problem, when I realized that there's this 2025, it's a square, right? So I had some idea of maybe try to visualize this square. So if you try to graph it, if you try to think of yourself as a point at origin, and the x-axis is the number of 1s you did, the y-axis is the number of 2s you did, I think you can actually correspond to the number of scores being the area under a curve sort of thing.
Yeah, you can. Yeah. Do you want to share your screen, Yannick?
Yeah, sure. Let's do this real quick. Yeah. So let me get this right. I think I want the x-axis to be number of 1s, and this is the number of 2s. So
you mean the y-axis, right?
So sorry, yeah. Y-axis number of stones, the axis number of scores. So let's think about how game would go. We start at the origin. We go up, maybe we put 2 stones here, and then we score, right? When we score 2 points. So the 2 points we score is like, we can think of it as like a small rectangle beneath the curve. And then we can go up more, like maybe we go up to 3, we score again, we get, then this corresponds to this curve, right? So like eventually, like it'll probably look like this, like maybe this is the end. Then the score we get is basically the entire area under this curve. And we know, and the number of moves we did is basically how long we travel like on top, or basically it's like you can actually think of it as a 1/2 of the perimeter of this shape. So that is like maybe a perhaps more intuitive reason why we can do a square to maximize our area, and why we can like just like chip off a little bit on the top to get to whatever we want. Yeah. So that's like one thing I realized like after I solved the problem, but I find it pretty neat.
Yeah, I mean, this diagram also shows the symmetry between the 1s and 2s, right? Because if you just rotate the diagram 90 degrees, then it's like
entirely symmetric.
Still the area, so everything's symmetric. It's basically saying like if you swap the 1 and the 2s, if you reverse the sequence and swap the 1 and the 2s, your score is still the same because you're always counting the same thing.
Yeah, exactly.
I think with this, you might actually be able to ask, well, how many sequences? Like, how many sequences of 90 moves give you 20 points? That shouldn't be too bad. Because all you really care about is like is like 2 rectangles or 1 or 2 rectangles on the corners that sum to area 5, and that should be pretty easy to compute.
You can have more complicated shapes in the corners too, right? Like you can have like.
Or yeah. But the point is, 5 is a small number, so.
Isn't that like that Young tableau thing? This is exactly the number of Young tableaus with.
It's not really a Young tableau though, because
Young
tableau, the number, the size of the rows are strictly decreasing usually, or at least that's by convention.
Wait, I don't remember, but yeah, something like that. Like it's some ways to put 5 squares in a corner.
Oh yeah, right. We don't actually look at both corners simultaneously. Yeah. Okay, I agree.
But for large numbers of 5, I guess it doesn't work because you still have the condition that you can't go past the boundary, right? Like
yeah. I mean,
you would need to compute the number of Young tableau on n elements in order to do that in general, and I think this is a very difficult problem.
Yeah,
I'm aware. I think it's related to partitions. Actually, yeah, it is partition number, which is.
Yeah, I think just partitions. Yeah, in fact.
There is no closed formula for that, as far as I remember.
Yeah. I guess if the Young tableau goes too, like if the things still go too far, you just have less moves, like less maximum number of moves.
Yeah.
So that's nice.
Okay, so guys, let's close up about here. So for the audience, I think this is such a cool problem to end, and I think the best part of this problem for these 2 different approaches is how do they reform the question. One is reform the question by counting basically the orders, right, between 1 and 2, and then the second one is considering these areas. You guys can, close this up, think a little bit more, and digest. And that will be the end of today's show. And everybody, good night.